If a nuclear bomb exploded in space, how far would the shockwave go? The beginning of the 1960s was a period of high tension during the Cold War between the Soviet Union and the United States. On August 30, 1961, Nikita Khrushchev announced the termination of a 3-year moratorium on nuclear tests. Already on September 1, the Soviet tests resumed, marking the beginning of a series that included the explosion of Tsar Bomba, the most powerful thermonuclear weapon in the history of mankind. In response, U.S. President John F. Kennedy authorized Operation Dominic. It was the largest nuclear weapons test program ever undertaken by the states. Operation Fishbowl was part of the Dominic program and was a series of high-altitude nuclear tests. In turn, the Starfish Prime project was a part of Operation Fishbowl. Starfish Prime is one of 5 nuclear tests conducted by the United States in space and the largest one among all conducted in outer space. It is noteworthy that the event was preceded by a failed start. On June 20, 1962, the launch vehicle, a minute after the start of the flight at an altitude of about 10 kilometers, began to fall apart. The landfill security officer ordered the destruction of the rocket. On July 9, 1962, the Thor rocket carrying a thermonuclear warhead was launched from Johnston Atoll, located in the Pacific Ocean, about 1,500 kilometers southwest of Hawaii. After almost 14 minutes, an explosion occurred at an altitude of 400 kilometers above a point 31 kilometers from the atoll. The capacity was about 1.45 megatons of TNT. For comparison, this was around 40 times less powerful than Tsar Bomba. The Starfish explosion caused a large electromagnetic pulse, much larger than expected. Because of this, many devices went off the scale, which made it difficult to obtain accurate data. In addition, civilian infrastructure suffered as a result. In Hawaii, 1,500 kilometers from the projection of the explosion point, hundreds of street lamps were knocked out, many active alarms went off, and telephone service failed. After the detonation of the bomb, bright auroras were observed in the conjugated region at the equator in the affected area, as well as on the opposite side of the planet. The lights were truly huge, they could be seen in a radius of thousands of kilometers. The electrons generated by the explosion are very light and quickly move away from the place of detonation. In motion, the electrons are exposed to a magnetic field, so they float along the lines of the Earth's magnetic field and dumped into the upper atmosphere. At an altitude of about 50 to 100 kilometers, they were already stopped by Earth particles. Atoms and molecules absorb the energy of electrons, thus creating an artificial glow. Other high-energy electrons created radiation belts around the Earth. The military became very worried when, as a result of a meeting with the belts, 3 satellites failed. In the following months, artificial radiation belts led to the failure of at least 6 more satellites. It is likely that in addition to effects such as a powerful electromagnetic pulse, a very bright aurora and dangerous radiation belts should be a shockwave. A shockwave created by a nuclear explosion is generated by the rapid heating of air, water, or rocks near a bomb. During detonation, occurring gamma and X-rays come into contact with the surrounding matter. During interactions, part of the energy is transferred to matter, heating it. Heated matter expands, generating a shockwave. That is, radiation from a bomb detonated in almost perfect cosmic vacuum must go a long way before being absorbed by matter. As a result, the shockwave in space is so small that it can go unnoticed. Leave us your thoughts in the comments section.